Hi, everybody. Welcome to this talk with Gopal Erinjippurath. He is the CTO and head of product at Sust Global. Sust Global is a company focused on quantifying physical climate risk for financial institutions. And as I mentioned in my opening remarks today, financial institutions are playing an increasing role in climate, and they're taking steps to estimate, price, and disclose climate risk. However, this is not an easy task. You need to quantify risks from several different climate hazards across a portfolio of assets. Making these insights actionable and interpretable is also hard. So Gopal will talk about that and about ways to combine climate models with on-the-ground, more real-time measurements. A bit about Gopal's background. He is coming to Sust Global from Planet Labs, which is a company that operates the largest commercial fleet of Earth observation satellites. And Gopal also has extensive experience speaking at many leading industry and ML conferences. Well, on to you, Gopal. Please go ahead and share your slides.
Yeah, thanks, Eugene. I gather my slide should be up now. Are you able to see it, just to confirm?
Yes, you're good now.
Awesome, thank you. Hello, everyone. Delighted to be here. Thank you, Eugene, for having me at this first of its kind conference, talking about commercial applications of climate science and related machine learning tech. And it's great to be presenting to you all. So I head up tech and product at Sust Global. I'm talking to you about scalable scenario analysis using global climate models. So in a nutshell, at Sust, we are building a company that challenges the lack of transparent and usable climate data and reinventing how we assess and adapt to the changing climate. So we've developed a proprietary tech stack to transform complex climate science into easy to understand actionable insights using cutting edge geospatial machine learning techniques. So we work with some of the biggest financial institutions, enterprise corporations, and investors, and help them to more accurately assess climate risks and discover sustainable business opportunities. So my goal in this presentation is to tell you a little bit more about the tech and provide some broader context around climate data, which is kind of what we're all dealing with today towards making actionable insights. So a little bit about me, I've spent the better part of the last 15 years working on enterprise software applications, worked on data-intensive applications in video and imaging early in my career, and then transitioned into geospatial data in the last 6 to 7 years. Here are a few venues where I've had a chance to share some of the research that myself and my teams have been involved in, and delighted to be adding this great new venue to that list. So, a rough outline of what I wanted to talk about is do a quick intro to climate modeling. I can spend multiple days talking about it, but I have limited time here. And then talk a little bit about the roles of scale and resolution, which I think are critical into understanding the actionable use of climate modeling. And then I wanted to touch on a couple of machine learning driven aspects to climate adaptation, which is resolution and validation. And then we'll have a few takeaways to wrap it. So in a broad sense, right, climate modeling, the way to think about it is largely a circular function or a circular modeling problem. It always starts with socioeconomic development. So compared to 100 years ago, the big thing that has changed in the Earth's environment that's led to changing patterns of climate is socioeconomic development. And that's normally through different, modelers in the climate space tend to map it through scenario assessments, which is what does the world look like between now and close of the century in terms of changing land use, changing energy use. And those are normally the main sources of human greenhouse gas emissions and air pollutants that interfere with the Earth's climate. So greenhouse gas emissions include carbon dioxide from combustion of fossil fuels, deforestation, methane from livestock, and waste fills, and fossil fuel explorations. So the projections of the future energy and land use and associated emissions that are derived from energy economics and land use models are what are the central components of what are called integrated assessment models. So that's essentially going from human activity to what we are doing to the environment, which is what the emissions piece covers. And normally the emissions end up in the atmosphere, changing the Earth system, and that leads to climate change. And that leads to climate impacts, which is essentially characterized by rising temperatures, changes in precipitation, humidity, and fundamental climate variables that are driven by radiative forcings in the climate system. So the Earth systems models built on top of these climate change projections create patterns of change in acute hazards, which is what impacts us humans. So those are the climate impacts, and that normally leads to migration patterns, different forms of adaptations in socioeconomic development, and then you have the cycle. So one way to think about it is climate change and climate impacts are largely in the realm of climate adaptation, and socioeconomic development to emissions is kind of the mitigation pathway. So people often ask, how do you distinguish between physical and transition risk in the context of climate change? I often, the simplest way to categorize that is physical risks are kind of what the environment and the Earth does to us, and transition risk is what human population does to the environment. So if you want to study more about this, there's this great census toolkit, which has like a great introductory set of presentations around climate change scenarios. And this is kind of like the underlying fundamental, which is going from socioeconomic development to actual impacts. And that's what's packaged as a set of assumptions in what are called climate scenarios. So, it's interesting to think about scale. So when you look at it from a climate modeling and Earth systems perspective, almost all the modeling is at a global scale, because this is a connected problem where you're bringing together the different parts of the Earth system, the land use system, the cryosphere, the atmosphere, and then the water ecosystem together. And that's assessed as like a whole. Unfortunately, when you do global assessments, you normally have a high level of positional uncertainty. And when you do projections, maybe in the near term or in the historic context, you kind of have good backtesting and you can come up with some kind of characterization of temporal certainty. But as you go out in the future, there's rising temporal uncertainty. So global climate models kind of fall in the low spatial resolution realm, which is kind of like at the global scale. So large scale coverage, but lower resolution in terms of spatial footprint. And what we have learned through the studies on climate adaptation is that when it comes to decision making, it's normally at the asset level. So business decision making, whether it is assessment of loans, whether it is analysis of mortgage portfolios, whether it is the assessment of insurance premiums, all those kind of financial business decision making often happens at the asset level. They care less about the global footprint, but more around what is happening at a specific property, what is happening at a specific land parcel. And that requires a very high spatial frequency. And in order to do that, what we've spent a fair bit of our time developing is asset level geospatial analytics, going from lower resolution, long time horizon assessments to shorter time horizon, high resolution spatial asset level assessments. So therein lies like a lot of promise in terms of bringing in global climate models into the functional loss modeling and business decision making functions. And the critical piece is, at that point, you can also start using a collection of different geospatial data sources. So it's a historic exposure of risk, which is kind of what helps for model validations, the early warning systems that allow you to understand what's happening in the near term, and then the climate models that allow you for longer term projections. And together, these three data sets are kind of what bring together climate intelligence, and that's what enables business decision making in the verticals in the financial domain. So in order to do that, fundamentally, you need to think of climate as like a geospatial big data problem, and geospatial machine learning becomes like the critical component there. So the open challenges we have seen in terms of getting this data into climate adaptation is asset level assessments and validation of models. So I want to touch upon a few techniques related to each of these. And both of them have machine learning related components, which are interesting and exciting. And it's a new space, new domain, lots of exciting opportunities for interesting tech developed by people like you in the future. So to take a higher level view, here's an example of climate projections. This is from one of the leading climate models. And later this year, there is the CMIP6 kind of framework, which is like the latest generation framework for model intercomparison between different research organizations. They're coming out of the assessment report, which is the AR6. And this is one early projection based on one of those models. And it tells you, like what you see in black in the center or towards the left is the projection, how well the models track the historic observations. And you've seen some version of this graph whenever you hear about climate modeling, which is warming and what has been the historic warming. So the exciting problem that all the climate models try to seek and provide answers to is on the right side of this graph, which is if you bundle together assumptions on socioeconomics, going back to the climate modeling cycle, when you bundle those assumptions together across different scenarios, what does warming look like? And this is like the baseline on top of which you can then do projections of different kinds of hazards, wildfire hazards, flooding hazards, cyclone modeling, sea level rise modeling. All those are capabilities you can build on top of it. So fundamentally, this is like saying across different scenarios, you have different kinds of warming. What you see in red here is the scenario, which is the track we are on today, which is business as usual. And it's categorized as the SSP 585, which is saying 8.5 additional watts of energy towards the close of the century for every square meter across the Earth's surface. And that leads to pretty high warming. And there are two other scenarios which are gaining some traction in the climate community, which is around the middle of the road scenario, which is SSP 245, which is if you did some amount of climate adaptation and mitigation, what does the world look like? And then SSP 126 is what people like to call the green road, which is if you did the heavy amount of greening and mitigation and adaptation measures, which is kind of what is coming through like the recent White House briefings in the United States, as well as a lot of actions across the world from leading governmental bodies. Then you're getting to some regulation that pushes us closer towards the blue line, which is the green scenario, where the warming is lower and it has lesser impacts in terms of climate projections. So that's like the high level summary into how to look at like these climate models and what they can tell you. So what does that mean for us? And what does that mean for businesses? Oftentimes that manifests in observations we've seen, right? In the last 5 years, we've seen the highest incidence of like wildfires across the Pacific Northwest. 2020 in particular was remarkable. It had the most active fire year in recorded history for the West Coast of the United States. And this is like a summary plot that was presented by NASA talking about cumulative fire detections derived from the NASA MODIS satellite constellations, which can measure an L3 level product around fire projections. So what it tells us is if you have this level of warming over the course of time, then you should be expecting some pretty severe manifestations of that in the physical climate, which manifests as physical risks, which is kind of what you see in these form of wildfire observations. And then if you project that out into the future, you can come up with models on what wildfire risk looks like. So, California, for example, has had like some pretty significant wildfires in the last 3 to 5 years across the state, and they've been pretty devastating. So in the last year, for the first time in recorded history, in the whole sky of like San Francisco was orange. And this was largely around September when there were wildfires all across the Pacific Northwest, and the aerosol drift from those fires into the atmosphere of the San Francisco Bay just made it have this orange hue. So it kind of looks apocalyptic, but then if you look at the climate models, you can get to understanding better what is actually going on. So here's a simulation based on the same model that I showed you earlier with a wildfire projection on top of it. So over the course of like a 3-year horizon, you can then see month over month what does the projected footprint look like. Most of the climate models project, at least for the Pacific Northwest, a higher amount of wildfire in the months of July, August, September, and some in October. And that's what you see in this animation. And this is kind of like the projection map to the grid cells. So on the ground. So in the geospatial context, this is kind of roughly at like a 0.8 degree resolution. So in the across the equator, that translates to around 80 to 90 kilometers on a per grid cell along the edge. So that calls for the need of like, what can you do actionably at the asset level using that kind of data? Not too much, because that's essentially saying an entire zip code has one value, or a good collection of zip codes has one value. And if you want to get to the asset level, one of the things you need to do is get to super resolution. And that's an area which the machine learning community has invested a lot of time and come up with some remarkable innovations in the last few years. They've been largely used on photorealistic imagery, but there are some interesting ways we can adapt that to super resolution that I wanted to tell you more about. So the big challenge with with the projections is that if you want to get to higher resolution, you can't just use like a smoothing operator or like a bicubic interpolation, because that almost works like a low pass filter on top of your image, and not very useful. In order to quantify the benefits of like reducing carbon emissions and related amount of physical risk adaptation measures, you need to get to like higher resolution projections at the asset level. And that's kind of where as a problem framing, we would start, which is if you took 1 month from a climate projection or like a year's aggregate climate projections, how can you get that to like a higher resolution or like a lower scale? And this is kind of like the ground truth you can look at, which is what the NASA MODIS satellite gives you in the context of active fires. So this is an L3 product. It gets you to 0.1 degree resolution, and it's at 1/8 the resolution of what the climate models project. And it tells you actually what was going on in those same 3 years, 2017 to 2020. So it gives you like a ground truth data set that you can then start building on top of. So in addition to just wildfire projections and wildfire observations, one interesting data set, or a couple of other interesting metadata layers, are burnable land index. So at any point in any geospatial context on any parcel of land, what is the amount of burnable land in there? If there is sand, it doesn't burn. If there's forest, there's a high likelihood it'll burn. So you can construct a burnable land index using that. And you can also come up with temperature deviation. So most of the wildfires are in areas where there is increased amount of deviation in temperature, not absolute temperature. And then that can be fed into any kind of super resolution capability as an auxiliary signal. And these are two additional layers which are geoscience driven that can be fed along with like the higher resolution signal for doing super resolution. So when you look at bringing super resolution related computer vision techniques into the climate modeling realm, here are some design goals. So fundamentally, you can't do transfer learning. The reason for that is most of the existing super resolution techniques are super resolved on very large data sets, and they're on a very different kind of imagery. So they're not geospatial data sets, they're not geospatial imagery, and they're normally photorealistic. So how do you efficiently learn on small data sets? The second complexity is in resolution scalability. So how do you go from, if you doing a 2x super resolution to a 4x and 6x, how do you scale that capability when you have more data? And the third component is around generalization. So how do you get to modeling capabilities where you can run a model using data from the US and from Australia and from parts of Asia, and then help use that model for projecting in multiple geographies? So how do you do that intelligently? And then how do you increase the extensible geospatial input? So today we're using, we started with using temperature, but then temperature deviations, then how do you augment that with like a new layer? So those are kind of enabling the super resolution capability to scale on the risk modality, on the spatial scale, as well as on the resolution. So here's kind of like the workflow that we arrived at using the modus related data. So if you have the fire exposure data at 0.1 degree resolution, you can then create a 0.8 degree resolution version of that through spatial aggregation. And that's kind of what you would provide as the input to your model. You would then use the temperature deviation and burnable land index as auxiliary signals on top of that, and then feed that through a network of alternating convolutional and upsampling layers. So as you upsample, you're intelligently upsampling using the additional metadata and using the spatial footprint of what wildfires look like. And this is the way we can train the network. So the exciting thing is once you build out like the baseline of this, you can expand that to doing higher resolution, super resolutions. So going from 2x to 4x to 8x. And that's through adding additional learning layers in between the initial and the final layers. So that's how we've expanded this to like 8x. And what does the model actually learn? So here is an animation, and for some reason it starts at 85. So this is where it starts. So initially it's all noise, but as the weights learn iteratively, you get to filters in like the first layer, which are 9 by 9, and they kind of represent notch filters, edge filters, and indicative elements, which tells you like the network is learning from noisy data into actually identifying fire pixels where there are active fires and discriminating them through gradients. So here's kind of some qualitative model evaluation studies. So if you look at just like the Pacific Northwest at 4x upsampling, so that's essentially showing you something at like the 0.1 degree, and then you were to bring that to 0.4 degree resolution, then you're looking at the fire originals at the top right. That's the original. This is the downscaled image. You feed that with deviations in burnable land, and what does the projection look like? That's essentially giving you the result from the model. And if you did just bicubic interpolation on the original data set, you're essentially getting to something which is really washed out and very low resolution still, but it's like running a low pass filter on top of your high resolution signal. So that's kind of what you see here. So the big difference is when you use the fire super resolution network, which is what I described before, you can detect as well as track the magnitude. And when you do bicubic interpolation, the detection's reasonable, but the magnitude is really off. So it's hard to make it actionable and some data that you can act on. The other exciting possibility is then you can apply it to future years and future months and then see what that looks like. So you have like the CMIP related data, which is coming from the Earth systems and the climate models, and then use a similar temperature deviation and burnable land index and use that for projections in the future. So that's where you've learned the system on observational data sets, used a very comparable data set for projections, and then you're able to apply that for forward-looking projections. So the learning happens on historic observations, which is satellite derived, and the projections happen on climate modeling derived outcomes. So if you want to read more about the techniques and like some quantitative assessments, you can go to this link, more in that paper there. There's also a recorded talk. And next I wanted to transition, seems like I have a few more minutes. So I wanted to transition to this other topic of model uncertainty. So if you went to like the model intercomparison project page, where the leading research institutions across the world are like working on different aspects of climate modeling and scenario assessment, one of the things you will see is on the data side and data user side, the climate model diagnosis is like a significant topic. And what that's essentially saying is, if you're trying to do diagnostics, the goal is to evaluate the climate models and capture and characterize the model uncertainty, because the models are becoming really complex and they're all dependent on some initial assumptions that you're making. So disagreements are often, and the simulations have variability which is poorly understood. And in order to make trustable signals, the bigger challenge is how do you do the right level of characterization of the uncertainty, and how do you bundle together models which come from a similar lineage and look at assumptions made across multiple models. So in the Earth systems community, that's often referred to as model ensembling. That's a technique we use as well. But when you ensemble, how do you capture the uncertainty across the models? And here's like a paper that that's been published in the last year that I just wanted to feature because I feel it has some really interesting smarts that are machine learning derived. And what it tries to do is distill a creative way for weighting the simulations from multiple models in an ensemble. And there are a couple of exciting factors that it brings in. One is benchmarking the historic performance against actual observations, similar to what we've done with super resolution. But the way they do that is they create a diagnostic metric, which is indicative of, for a specific model, if it were to project out for the last 10 years, what the temperature deviations or the temperature projections would look like. How well does it correlate with other models in the model bank? And how well does it correlate with observations? And that's kind of the diagnostic metric. And through that, you can understand what the tree of models looks like and how much interdependence there are between multiple models used in the ensemble. So here's the exciting methodology, which is like saying, you bring, if you were to look at like 30 different models that all did temperature projections, and you were to use that diagnostic metric as a means towards capturing a generalized distance, then you can then create a dendrogram which tells you how much interrelationship there is across the different models. And the ones which are branching more towards the left are more dependent. The ones branching more towards the right are less dependent and have more unique predictive power. So that's a way to distill and intelligently aggregate different models. And this is one example where they've done it for temperature. There are exciting ways this can be adapted into different kinds of physical hazard as well. So those are two exciting dimensions. So, to wrap, like, here are some takeaways. Fundamentally, climate modeling is hard, complex. It's highly interdependent on many different variables. And the way to think about it is framing it as a geospatial big data problem. And oftentimes, when it comes to business decision making, the global scale is exciting, but it doesn't lead to actionable insights. You need to bring it to the property or asset level. And a couple of techniques there is super resolution and aggregation. So when you super resolve, do it, but do it intelligently. Don't just use bicubic interpolation, and use the right metadata layers like we've tried to do, which is leading to some very exciting results when you do validate. And secondly, when you aggregate responses from different models, do so with caution and take into account the amount of correlation between the different data sources and how well they match up with observational data sets. So, if you want to read more about these in this more work that we've published on our blog at Sust Global, here's the link. And then we're constantly hiring for folks who want to work at the bleeding edge of like data, machine learning, as well as climate modeling, serving financial enterprises. And that's kind of been our mission, connecting frontier climate science to actionable climate intelligence in the financial services. So if you're like a data scientist or a data engineer or a backend engineer who's excited about these kind of techniques and wants to dive in deeper, feel free to reach out. And here are some places where you can find me. You can also message careers at Sust Global, or happy to just talk about the technology as well. So with that, I think I'll hand it back to Eugene to get into the Q&A part of the session.
Yeah, thank you. Thank you so much, Gopal. Excellent talk, and good to see recent advances in ML being applied to climate, the super resolution techniques, and so on. So one question is, could you clarify a little more what kinds of business decisions do your clients make based on your model predictions? And I imagine that might be different for different types of clients.
Yeah, absolutely. See, fundamentally, what's happening is across the financial services ecosystem, there are multiple headwinds. One is that around regulation, which is if you have assets which have a tremendous amount of physical risk exposure. It's something that you want to screen for and enable mitigative measures. And that's part of like a range of different regulatory outcomes that are coming out today. And we enable those kind of outcomes based on techniques like this, which is asset level assessments, connecting into mitigation measures, which can be served. Secondly, it provides for like a screening tool. So if you're looking at a very similar group of assets, which have very different kinds of physical risk exposure, how do you enable the financial services industry to pick and choose assets and sustainably allocate capital in an intelligent way using data sets and data streams and climate-related insights like what we are producing. So those are two broad avenues where we're providing a fair bit of intelligence today.
So it sounds like financial services companies use this to decide where to allocate their money. And I guess companies whose assets are under threat like use this to decide what to do about it and like to change their business strategy to maybe like shift away from the particular risky areas.
Right.
Yeah, that makes a lot of sense. Obviously, like there is a lot of money at stake for the players whose assets you're assessing for risk. So, which is why I guess you guys are a successful commercial business.
Yeah, absolutely. And just on that, right? Like just in 2020, it's upwards of $100 billion in like asset level losses across the US. It's like a huge number, and like it's something that people are beginning to take note of. And it's just increasing. So, we're bracing ourselves for like the wildfire season this year, and then the increasing amount of like cyclone and flooding damages in other parts of the US. And that's just in the US. So globally, that number's a lot higher.
Yeah, I think I remember seeing in some of the reports about climate risk assessments, basically the amount of money at stake here is not just trillions of dollars, it's more than that. Like especially in the business as usual scenario, like the physical risk represents something like 25% of the world's GDP. So like, of course, the people who are owning this don't want to lose, 25% of humanity's GDP.
Right, exactly.
Yeah. Okay. Another question is, to what extent is physical risk assessment, like the stuff that you guys are doing, bottlenecked by availability of data versus better machine learning methods versus better physics modeling versus just deploying it to the businesses that use it?
Yeah, I feel like there is a pretty equal spread. So I feel like the challenge is not in there being data. I think the challenge is in making that data interpretable. So one of the big challenges, we as a community of like machine learning and data folks can help with is we fundamentally deal with data every day, right? That's our bread and butter. How do you make that palatable to an audience? So one of the things we have seen is in the financial services space, people are aware of geospatial data, but they don't really know how to deal with it. Like they don't know how to work with spatial context very effectively. So that's an area we've invested a fair bit of time in terms of making the data effective. Fundamentally, they're used to seeing time series. Making the data palatable to that audience is something which, as a data and machine learning team, you often need to invest a fair bit of time doing. And I think the second piece is also around you might have a lot of data, you might have the right analytics, but the interactive nature on like the user experience on the solutions needs to be very crisp and effective, because most of the times in the financial services space, they don't look at just climate change in isolation. They look at many different parameters. So attention in the consumer space is like, or the client space is spread pretty thin. So how do you get them the right information in a way they can pick up really quickly? And I don't think that's just purely an ML problem. It's a user experience problem. And there are creative ways in which we can solve that. So we're kind of investing in all those three fronts. And the way I like to think about it is the science piece, which is kind of broadly what we've touched on here. Then there's the engineering piece, which is how do you make that effective and useful? And then there's a product piece, which is what's the engagement layer? What does that look like? And you kind of need to innovate on all three to make meaningful contributions in the space in the near term.
So it sounds like one of the challenges is basically like bridging the gap between the climate models and the business people. Like showing it in terms of their language, the language that they speak, financial language, right?
Right.
Awesome. Another question that somebody just submitted, are you working on modeling risks outside of fires, and how might modeling approaches change when considering the different environmental processes?
Yeah, great question. I feel like, the fires are one of the assessments that we've done. We are looking at multiple other kind of physical hazards. That's one of the other challenges, right? Traditionally, this community has been very single hazard focused. But the reality is, if you're looking at like a pool of assets spread across the world, the different locations have affinity to different kinds of hazards. So hazards by their very nature spatially non-stationary, so different areas have different exposure. So we're looking at that, and I think some similar techniques can be applied. There are research groups focusing on flooding, cyclone-related damage, and the two techniques that I described, there is an analog of that in those worlds as well. When it comes to model aggregation, when it comes to super resolution, and those are all things that we're actively looking at.
Got it. And that actually brings me to a point that somebody raised, that Dr. Sekou Remy raised in the panel. He mentioned a type of risks that that wasn't on my mind at all, which was the risk of locusts in East Africa. And I suppose there might be more types of risks that many of us just like don't know exist. But when somebody mentions them, you're like, well, of course it exists. Are you guys modeling anything like that might be non-obvious to?
Yeah. There are multiple of those that are on that are possibilities we're actively exploring. We've limited it to, like, there's an element of, like, in the future this is going to be a more holistic system where you're looking at many different dimensions, but there's some dominant vectors, right, which you got to get done first. And I feel like the industry as a whole is catching up to that. So today, even doing this in a holistic way for wildfires alone is kind of hard. So how do you go from that to, like, maybe go from the walk, crawl, run kind of model? So before you get to locust, you kind of want to get to, like, the big loss events. And in the US, that's fires, floods, and cyclones.
Got it. So another question somebody asked. So providing the actionable and understandable data is important to understand the problem, but the person is asking, are there other ways in which Sust Global is contributing to solving climate change? Basically, are you guys focused entirely, I guess, on risk assessment, or are you also exploring other areas?
Yeah, we see risk exposure as like the foundation, because I feel like that's kind of, one, it's immediate. It's a critical business need, and it's a place where there's the immediate need for data translation from the climate-related capabilities into actionable insights. I think there are multiple other dimensions. So I mentioned a little bit around transition risk. So that's kind of like, how do emissions, for example, one dimension there is emissions, and how do you track the emissions, just like you track, like, the risks from different kinds of physical hazard, and that's also a geospatial problem. So those are all frontiers that we see down the horizon, and they all relate to potentially great ways by which we can provide actionable insights and information downstream to the financial services space that we're very excited about. So yeah, more to follow on that.
Makes sense. And to tie into that a little bit more, are you involved at all with transition risk, which is, I guess, the risk to business models rather than the risk to physical assets?
Yeah, we've seen transition risk as like a fairly complex problem, and it bundles together many different product dimensions. Emissions tracking is one, legislation and legal is another, and stranded assets is another. So we've looked at some specific. We're definitely exploring that as like potential avenues for the future. Although right now we got our hands full with the impending work on physical risk. So something for us to follow in the future.
Yeah, makes sense. Thank you. So yeah, I guess for people in the audience, transition risk appears to be a comparatively neglected space. So go do something in it, people. So another question from the audience: how do you effectively communicate the uncertainty when informing the business decisions?
Yeah, great question. So there are two dimensions there, right? One is how there's the model uncertainty, and then there's the system uncertainty. And the way to characterize each one of them is model uncertainty can be often packaged or presented as through data validation efforts. So if you pick that model and you did a back test over like the historic 10-year, 20-year horizon, you then get to some meaningful indicators of the performance. And here's the thing to keep in mind, right? No model is like perfect. No model provides, if it provides some meaningful information, then it's usable. And normally that is the back testing allows you to understand, okay, historically where you could benchmark against observations, how well does that do? And then the system level uncertainty is kind of characterized by what I described with the aggregation phenomena. So how can you package the uncertainty of an ensemble relative to the uncertainty of a single sample or one of the specific models in the ensemble? And ideally, when you bundle them, your uncertainty should go down, which is kind of what most consensus protocols do, right? Essentially tell you if you have like multiple people saying yes, then most likely the answer is yes, compared to one person saying yes. So that's the system level uncertainty metric that you work on. And both of these have an intelligence component or an ML component to it. So that's the way those are the approaches we have looked at when it comes to talking about uncertainty.
Got it. Thank you. And maybe can you also talk a little bit about what is your tech stack? Like, what might someone expect when coming to work for you? What sort of expertise are you looking for?
Yeah, absolutely. So the way fundamentally this is like a lot of Python, and we have JavaScript for like the front end and the UI elements. I would say in the context of like languages, you shouldn't expect something very different from standard analytic applications. The big difference is when it comes to data storage and dealing with like the larger data ingest pipelines, you're looking at a lot of geospatial context. So understanding, databases which have geospatial extensions, which is now pretty common. Most analytical data stores have some form of that, and some transaction-oriented data stores also have it. So that's one thing. And then being able to do queries at scale is something we're investing in. So the tech stack has that component. So I would say it's largely like a full stack analytical application rather than transactional. So being able to do large scale ETLs, that's kind of what we are optimizing towards.
Got it. Yeah, that makes sense. Seems to be a common theme again, that like pretty much the tech stack at a climate tech startup is pretty standard compared to other startups, just with some amount of domain expertise, specific extensions, and of course, like working with people who know how to apply this tech to the domain. Right. Yeah, let's see. So I guess another related question to that would be like, what kinds of people have been joining your team? Like, where are they coming from? What's motivating them? I pretty much asked this of almost everybody.
Yeah. I feel it's there are two things. So one of them is we've seen the application of data and machine learning techniques in many different domains, right? In the last decade, I think climate is a fundamental problem for like our generation. And it has like tremendous impact. We are at the bleeding edge of that, doing these kind of capabilities that I was able to walk you all through. So the inspiration is normally how do you apply like the data science and the engineering skills into this kind of a critical problem, which is fast evolving. And it's a tremendous source of learning on multiple dimensions, right? Which is the product dimension, the science dimension, and then secondly and thirdly the full stack which is evolving of it. So we've been able to hire folks from like a science background, some of them who have spend a lot of time doing machine learning in other domains, who are inspired by climate, and then folks who worked in the financial services and who are exhausted looking at purely banking or insurance infrastructure, and they care about having more meaningful impact, and that background is very valuable to us.
Got it. Thank you so much, Gopal. So we're at time, and thanks again for this talk. This was great. So for everybody in the audience, see you in a bit at the talk with Terrafuse, which are attacking a similar problem from a slightly different angle.
Thanks, everyone. Yeah, really enjoyed the insightful questions. Hope to stay in touch. And thank you, Eugene, for moderating.